We're going to talk here about source and field coordinates. Electric fields, like other fields, are produced by sources, and we have to distinguish between the elements of charge that produce the electric field and where they are located, and the location of the points in space at which we wish to know the electric field. So we start out by distinguishing between these two, between source points and field points. We put down a coordinate frame. We look at our charge distribution, and so here is a kind of arbitrary charge distribution, and we can ask ourselves, what is the electric field that's produced by some small element of charge in this distribution? We ask this question because we know the answer. The answer is an electric field that is essentially Coulomb's law, but we'll show you that in a second. Now, first we have to be able to talk about where the charge sources of the field are, and we do that by specifying a position vector for each little element of charge dqs in the distribution. And then we need to also talk about the point in space where we are looking at the electric field, and we do that with another position vector, r sub f, f for field, and the result is we are able to locate both the sources with vectors r sub s and field points with vectors r sub f. These are both position vectors, and so they depend on your choice of coordinate frame, where you've put the origin of your coordinate frame. And the physically significant quantity then is not these two vectors themselves, but their difference. This is the difference which locates the field position relative to the source. As I say, once you have this position, this is the physically significant quantity because it is what governs the behavior of the law that specifies the electric field element that you're going to see at r sub f. And so we are talking here about a little element of electric field at some point in space out here. And what you see is that it's a vector field, a little vector element that's produced by element of charge dqs, that's this guy down here. And it is also, the strength of the field of that element is just your familiar 1 over the square of the distance, the inverse square law here. There is also this factor at the end, which is a unit vector constructed by dividing the vector r sub f minus r sub s by its magnitude. So this is a unit vector that points away from dqs. So that's what this unit vector is. And you'll often see the unit vector written, you'll see it written as n with a hat on it, or a hat often be used for unit vectors. And the along with the sign, sign of dqs, it specifies the direction of the electric field. And you see, if this were a negative element of charge, then when we put in a negative value for dqs, the actual direction of the electric field would be in the opposite direction. It would be in the minus n direction. That would be the attractive, showing you that a small test charge placed in the electric field up here would be attractive towards here, whereas if this is a positive element, then a small test charge placed up here is repelled away from the dqs. So that's really all there is to this, and it's quite a powerful tool that's placed in your hand, because if you want to know the total field at this point here at r sub f, if you want to know the total field from this complicated distribution of charge, or any distribution of charge, all you have to do is calculate the elements of electric field from other elements of charge, and just repeatedly use. I'm not getting this very straight, am I? It's supposed to be a nice straight vector. Sorry about that. And you're just going to do this for all the elements of charge and keep adding vectorially here to get the total contribution from this distribution of charge. So it's just straightforward summation procedure. A summation procedure that you can do in a spreadsheet, just keeping in mind that it's vector addition and you have to add components together so that you're dealing with sets of 3 numbers here at the field point. And you can now handle, in principle, quite arbitrary distributions. Now we're going to look at some of these some simple distributions that allow us to use not just numerical integration but calculus, and so we'll be able to obtain nice informative algebraic expressions for what the field is up here when it's produced by normally these will be rather simple or highly symmetric charge distributions that we talk about, but more about that in a later module.